Welcome back, guys. Sounds weird, but it's our last section in Chapter 4. We're going to go through 4.6 today. Again, please remember we skipped 4.2, 4.3, and 4.4. If you do want to learn more about those, you can read them in your book, but for the interest of time and the content of this algebra class, we'll be skipping them. So we're in our last section, 4.6, and we're going to dive more into probability in this section. We did a lot of probability stuff in 4.5. We learned about ratios and proportions in 4.4. And we're going to continue with probability in 4.6. So what I want you to do is pause the video and figure out the probability of drawing this card out of a deck. Nine of spades. What is the probability of getting a nine of spades if you had a full deck? A full deck reminder has 52 cards. What's the probability you pull the nine of spades out? Well, you could probably tell me after doing that the probability of pulling a nine of spades is 1 out of 52, right? Every deck of cards has one nine of spades in it. There are 52 total. We talked about this in 4.5, right? Theoretical probability. The probability of a favorable outcome, I select what I want. There's one nine of spades out of the total sample space, aka the total number of cards. Okay, nothing really new here. If I asked you what's the probability of just picking a nine in general, you tell me 4 out of 52. There are 4 nines in a deck of cards, again, 52 total. If I said what's the probability of drawing a spade, you would tell me 13 out of 52, because there are 13 spades in a deck. Again, 52 total cards. Nothing really new to see here. But here's where 4.6 gets pretty interesting. What about finding the probability of me drawing a nine of spades and a two of hearts? Well, you're probably thinking there are two different situations there, right? I could, if I had the deck of cards, pull out and see if there's a nine of spades, lay that card down, and then select another and see if it's the nine of hearts. Or I could take out the nine of spades, put it back, then try and pull out that two of hearts. Either way, I want you to figure out the probability for both situations. Try and see if you can do it. Okay? Hopefully you gave it a shot. You've unpaused the video, and you're probably kind of confused here. You're probably not sure about what to figure it out. Well, let's talk about both different situations here. The first situation, if I replace the first before drawing the second card, well, let's handle this one at a time, right? We said earlier the probability of drawing a nine of spades is 1 out of 52. I have a 1 in 52 chance. If you want that in a percentage, that is a 1.9% chance. 0.019 is a decimal. 1.9% chance I draw the nine of spades. Okay. Well, then I put it back in, and then again, I draw an A. It's the two of hearts. What's the chances of that happening? Well, there's a 1 in 52 chance I draw a two of hearts out of a full deck of cards. So 1 in 52, I pull out that nine of spades, put the card back, shuffle them all up, and then the card I pull is a two of hearts. So again, another 1.9% chance. So you might be sitting there thinking, okay, well, it's 1.9%. Or we double it, and it's 1.9 plus 1.9, so 3.8% chance. Well, not quite. You see, if I want to figure out the probability of both occurring, what I hope you recognize in your brain, the problem was saying the chance of this happening, of me drawing a nine of spades, putting it back, and then drawing the two of hearts. The problem with just saying that's 1.9% is if we think about it, it should be less likely. The likelihood of me drawing a nine of spades should be greater than the chance of me drawing a nine of spades, putting it back, and then drawing a two of hearts. And here's how you handle it. This is known as an AND probability. I have a 1 in 52 chance of drawing the nine of spades and a 1 in 52 chance of drawing the two of hearts. What are you going to do? Well, you're going to multiply the two together. with and probabilities, we multiply. So how do I figure this out? Well, I have a 1 in 52 chance for the 9 of spades and a 1 in 52 chance of drawing a 2 of hearts. 1 out of 52 times 1 over 52. Let me do it in the calculator here. 1 over 52 times 1 over, sorry, hit the wrong button. 1 over 52 times 1 over 52 is 1 over 2,704, which is the same as 0.00036 or actually it'd be 70. Sorry, I rounded wrong. Or in other words, a 0.037% chance that happens. Okay? So that's the percentages, but here's the point. Not only in probability do we want to do singular probabilities, but we want to do compound probabilities. The chance of me drawing a 9 of spades, putting the card back, and then drawing the 2 of hearts is incredibly unlikely, but we can calculate it by multiplying the probabilities together because it's an and situation. Okay? Let's talk about the second scenario here. What if I don't replace the card? Well, let's start at the beginning. What are the chances of me drawing a 9 of spades? Again, you know this is 1 in 52. Well, what if I just set the card down? What if I don't put it back in the deck? Well, there's only 1 2 of hearts in the deck, so there's only one favorable outcome. But instead of there being 52 cards, there's only 51 now, because I set it on the table. The chances of me drawing the 9 of spades, laying it down, and think multiply, and then drawing the 2 of hearts, you would multiply these two probabilities together. When I do that, I have a 1 in 2,652 chance of that happening, or a 0.0000377 chance, or if you wanted that in percentages, a 0.0377% chance. Okay? So what I hope you understand, what this little introduction is giving you, is what is compound probability. Okay, not only do I have a singular event happening, but what happens when I have multiple events back to back. Okay? So the summary and the definition I want you writing down is, if I don't replace the first card, it will impact the second. If I do replace the first card, it won't impact the second. If you do an action or take an action in probability, and it impacts you taking a second action, it is known as a dependent event. But if your first action does not impact the second, it is an independent event. Again, I do want you to pause the video and write these down. Dependent versus independent. What? I draw the card, put it back, then draw another. Independent. My first draw didn't impact my second. If I draw the card and set it on the table, then draw another, it is dependent. Okay? You can think of a couple different situations here. If I roll dice, right, and then pick them up and roll it again, does the roll of my first die impact the second? No, it doesn't. Those would be independent events. Independent versus dependent. Okay? Independent versus dependent. Again, some examples. Flipping a coin, right? If I flip a coin, will the first flip impact the second? No, it will not. Okay? That is an independent event. Dependent, again, a great example is drawing a card and just setting it on a table. So how do we calculate independent and dependent events? Well, this is a fancy way of writing, and I want you to write it down, but it's a fancy way of what we did with the cards earlier. If the events are independent, just multiply the probabilities. What you should think of here is I did what? 1 over 52 times 1 over 52. Okay? That's what we did earlier. To calculate a dependent event, though, it takes a little more work. You're going to have that initial probability, but then for the second, you have to account for the fact that A occurred. So this was us subtracting 1 from our total number of cards in the card example. Okay? In each situation, when you have multiple probabilities and probabilities, I would say, where you are multiplying 2 together, okay, independent, you go ahead and multiply them, but if the first action impacts the second, dependent, please make sure that you account for that occurring when multiplying your second probability. So suppose you roll 2 dice. What are the chances you roll a 6 on the first one and an even number on the second one? How do we solve problems like this? Well, if you feel confident, go ahead and try it on your own, but if you don't, we'll do it together. So if you feel good, pause the video and try it. Okay, so the first thing I see here, suppose I roll 2 dice. What are the chances you roll a 6 on the first and an even on the second? I'm thinking multiple probabilities. Combine that with the word and here, and I know some form of multiplication is going to be happening. Some form of multiplying the probability of the first event by the probability of the second. So now we need to think of if this is independent and dependent events. Okay? Does the first roll impact the second? Think about it like this. If I roll a die, pick it up and roll it again, does the first number affect the second at all? No, it doesn't. Okay? So what are the chances I roll a 6 on the first one? A 1 in 6 probability. There's 1 6 on a regular die, 6-sided die. There are a total of 6 options. One of them's a 6, so 1 in 6. Even on the second, well, there's a 3 in 6 chance I roll an even. Okay? Again, that sample size does not change from 6 because these are independent. So now I multiply the fractions together. I get 3 over 36. Which is the same thing as 1 over 12. And I find that there's roughly an 8.3% chance that you would roll a 6 and then roll an even number. Probably you're thinking in your head, maybe this is a little low. Where this is applicable to the real world is cards, Vegas, and gambling. Okay? You may not know it, but every casino game in the world has less than a 50%, except for one, which I think it's blackjack. Every single casino game, betting game in the world has less than a 50% chance of occurring. This is, if you walk away with nothing else, this is where probability applies. Every game has less than a 50% chance of success. Now, you might get lucky and you'd be the one winner, but now combine that with what we talked about in 4.5 with the law of large numbers. The more and more trials that happen, the closer that experimental probability gets to the theoretical. What's the moral of the story? You're not the only customer at Vegas. So you, A, don't have a likely chance at winning. It's at least less than 50%. Most are significantly lower than that, especially the lottery. But B, even if you are the big winner, there's so many people going to these casinos that over time, the casino will always make money because of the law of large numbers. Eventually, the large enough sample will go true to the theoretical probability, and the casino will win more often than it loses. Insurance is the exact same way, right? Why does life insurance make sense? Let's say my wife gets a $200,000 coverage if I die because I pay life insurance every single month. Well, am I going to pay enough over the span of my life to ever reach $200,000? Absolutely not. But the likelihood of me dying, which insurance companies actually calculate based on my age, weight, where I live, all that good stuff, the likelihood of me dying is not very high. So even if someone like myself dies and they have to pay out that $200,000, if they have enough other customers, again, the law of large numbers, they're going to make money on top. That's where you see probability in the real world. Fascinating subject. Okay? But this is for our Algebra 1 purposes. This is how you calculate and probability. We're not going to do the 2 students example because you all aren't in person. So that won't work, but we can look at the probability table. So sometimes we can see probabilities or data broken into a table and we can determine probabilities out of it, okay? So what do we see here is we have a few different categories. We have the type of job people are doing over here, and we have their political affiliation right here. So what do the columns mean? Well, there are 5 people who are executives and Democrats. There are 34 people who are executives and Republicans. There are 8 people, sorry, I should have made this a little bigger. There are 8 people who are independents and production workers. Okay, you get the idea. So sometimes we want to use tables like this to calculate probability. So I'm going to give you a couple examples. I want you to try them and then unpause the video and see what we come up with. What's the probability of someone being a Democrat at this company? It's probability of someone being a Democrat. Pause the video, each time I ask a question, figure it out, and then we'll talk about it. Well, let's think about it. What's the probability of someone being a Democrat? Well, you're going to take, for theoretical probability, the total number of employees divided by, as your denominator, and what is your total number of Democrats? Well, I have 5 who are executives, 63 are production, for a total of 68. So there's a 68 out of 140 chance that a randomly selected employee is going to be a Democrat. What is the probability that someone is an executive at the company? Well, hopefully you've paused it and gotten a chance to figure it out. There are 48 executives in the company. If we go across, we can see how many executives there are. And there, again, are 140 total people at the company. So you have a 48 and 140 chance of randomly selecting an executive. Okay, let's advance a little. What's the probability someone is a Republican and a production worker? Probability someone is a Republican and a production worker. You randomly choose someone, okay? Well, probability tables, I know we talked about multiplying earlier, but we're not going to do that quite here. Instead, what we're going to do is we're going to use the chart to find both. So the probability someone is a Republican and a production worker. Well, there are 21 production workers who are Republicans. And again, you have a total of 140 employees. So there's a 21 in 140 chance, given this probability table, that someone's a Republican and a production worker. Or that you select one person and they are a Republican production worker. Okay, let's try another example. What is the probability someone is an independent and an executive? Well, hopefully we have that total of 140. And then there are 9 independent executives at the company. So your probability is 9 out of 140. Okay? Now you might be wondering, why are we not multiplying anything together? You keep saying independent and executive. Please note what I'm saying here. We're only picking one person, right? This is just the categories they fit in. There are 9 independent executives. Okay, you might hear me phrase that as independent and an executive. But we're not going to multiply. That would be the situation where I said, what's the probability someone's an independent and an executive? Then you choose someone else and they're a Republican in production. That will get more into the multiplication. And we'll talk about that another day. But for now, we're just using the probability table. Now let's get a little trickier. What's the probability someone's a Republican executive given that we're only choosing out of all the Republicans? What's the probability someone's a Republican executive given we're only choosing out of only the Republicans? Well, you already know there are 34, you've gotten pretty good at this, there are 34 Republican executives. But I said I want to choose only out of the Republicans. So you could have seen it phrased as, what's the probability someone's an executive given they are a Republican? Well, now I've shifted my total. You see, I'm not looking at all 140 employees anymore. Instead, what I'm looking at is only the Republicans. So how many total Republicans are there? 55. So the chance that someone's an executive given that they are a Republican is a 34 out of 55 chance. When you hear the word given, or I change my sample space, I change my total, I pare down my group I'm looking at, this is known as conditional probability. When you hear me use the word given, or I am shrinking my total looking at a specific group, that is conditional probability. Let's do one more example. Again, please write down that term. If you didn't get it, go back, pause the video, check it out. Okay, given, what is the probability that out of all production workers, I randomly pull a Democrat? Given that I'm looking at all the production workers, what's the probability one of them is a Democrat? Another way you could say it, what's the probability someone's a Democrat given they are a production worker? Well, there are 92 total production workers, and I'm only looking at them. Again, what's the probability someone's a Democrat given they are a production worker? So that changes my total. How many Democrat production workers are there? 63. So there is a 63 and 92 chance that I randomly select a Democrat given that I'm only choosing from the production workers. Okay, I hope this makes sense. Email me if anything doesn't, and have a great day.